So, good morning everyone, and welcome. Welcome to Code as a Crime Scene. Today, I want to give you a different perspective on your code base. I'm here to investigate the traces we all leave behind as we create our systems. And you will see that there's a lot of valuable information in those traces. And it's information that's going to help us identify the code that's hard to maintain, the code that risks for defects, and the code that becomes a team productivity bottleneck. So let's jump right in and have a look at what we programmers actually do. We programmers, we don't write code. I mean, sure, obviously we do that as well, but that's not where we spend most of our time. If you look at the research findings, you will see that we actually spend most of our time making modifications to existing code. And the majority of that time is spent trying to understand what the code does in the first place. So the takeaway, at least for me, is that if we want to optimize any aspect of software development, we should optimize for ease of understanding. This is a challenge. Here's why. Have a look at this visualization. That's how most of the systems look, at least the ones I've been working with. And given this visualization, which parts are hard to maintain? Where will the bugs be? Are there any team productivity bottlenecks? Without more context, we just cannot tell. And this is a challenge that gets harder with the scale of it, because today's systems are developed by multiple programmers organized in multiple teams. And that leaves everyone with their own view of how the system looks. No one has a holistic picture. And this is an age-old problem, right? So we've been struggling with this for a long time in the software industry. And I would like to start by having a look at one of the traditional approaches to tackling that. And then we see the limitations of that approach before we move on to something entirely different, right? So let's start with complexity metrics. Have any one of you using complexity metrics today on your systems? Cool, so approximately 10-15 people, great. So we have a bunch of different metrics to choose from. And most of them go all the way back to the 70s. So this is an example. This is called McCabe's Cyclomatic Complexity, where you basically consider your program or your function as a graph, and then you calculate the number of possible paths through it. And the higher that number, the more complicated the code. And this kind of makes sense, right? Because it ties to one of the most limiting factors we have in programming. It's a cognitive factor, our working memory. There's really just so much we can hold in our head at once. So I would say things like McCabe's Cyclomatic Complexity definitely make sense. I also asked you, and it was just like 10 people out of all the people in this room that uses complexity metrics today. So if we have complexity metrics to identify the code that's hard to maintain, why don't we use them in our industry? I really don't know, but I know why I don't use complexity metrics. And the reason I don't use complexity metrics is because complexity metrics are pretty bad at predicting complexity. It's a bold statement, so please let me support it by reading a quote for you. Syntactic complexity metrics cannot capture the whole picture of software complexity. And what I like about this quote is that it's from a research paper. And what these researchers did was they took a bunch of different metrics like McCabe and Halstead's complexity measures, and they identified how well do these metrics perform on real-world code bases. And what they found out was that as soon as you start to control for the number of lines of code, those metrics don't add any further predictive value. Wow, the number of lines of code? That's a really rough metric. Is that really the best we can do? Let me read another quote for you. And this is one of my favorites because it's a little bit evil. The use of metrics to manage software projects has not even reached a state of infancy. So this is a quote by Robert Glass. And he's one of my idols. He's really great. And Robert Glass means that software is just so complicated, so open-ended, that we will never, ever be able to measure it. So what Glass suggests instead is that we rely upon our intuition. Now, as some of you may know, I actually have a parallel career as well. I have a parallel career within psychology. And as a psychologist, you just have to love the concept of intuition, because it's such a warm, fluffy human subject, right? But what is it actually? It turns out that how many of you have been working more than a decade in the software industry? So almost everyone, cool. So during that time, you have all built up a lot of expertise. And all that expertise is stored away in your head. Now, intuition, that's basically just something in the situation, perhaps something you see on screen or something you see in your code editor that triggers a recall of some of that information. So intuition is basically just recognition. The thing is, intuition is an automatic, unconscious process. And that means you have no conscious recall over what kind of information that gets retrieved. And that's kind of what gives the intuition its mythical qualities. But it also makes intuition extremely prone to cognitive biases. And even if we could somehow control those biases, which we can't because we are humans, intuition would still not do the trick. And the reason for that is that intuition doesn't scale. No matter how good programmers we are, there's just no way that our expertise is going to scale to hundreds of thousands or even million lines of code. There's really no way to do it. And in the software industry, we haven't come up with a good response to that challenge. So what I suggest is that we look into a completely different field. It's a different discipline, but one that faces similar, open-ended, complicated questions as we do. So please, welcome to forensic psychology. You probably all know a little bit about forensics already. Perhaps you've read about profiling in the news, or you've seen CSI, haven't you? Yeah. And I also bet that all of you have seen the movie Silence of the Lambs, right? Cool. Also bet that you all agree with me that Hannibal Lecter is the coolest character. Right? So the first time I saw that movie, I was extremely influenced by Hannibal Lecter. And I don't mean that, no. I don't mean that in a scary way, right? No, I was influenced by his forensic skills, not the other stuff. It's completely safe to have dinner with me tonight, I promise you. So if you think about it, it's actually quite amazing what Hannibal Lecter does. Hannibal Lecter sits there, locked up in his cage, and he receives information from the crime scenes. And based on that information alone, Hannibal Lecter is able to deduce not only the motives, but also the personality of the offender. And the first time I saw that movie, I was like, wow, I want to learn to do that. Years later, as I actually started to study criminal psychology, I got terribly disappointed. Because it turned out that those techniques that Hannibal Lecter had been using, they have a very serious limitation. It turns out they only work in Hollywood movies. Fortunately, we got some more scientific methods. So please allow me to give you a 2-minute introduction to geographical offender profiling. Now, geographical offender profiling is based on a very fundamental fact. And it's perhaps a bit surprising because it's so obvious. But did you know that criminals, most of the time, behave just like us? They go to the movies, they go to restaurants, they visit friends. Perhaps they even pick up the kids from school. And as they move around in an area, that's where they spot an opportunity for crime. Because for a crime to occur, there has to be an overlap in time and space between an offender and a victim. And what that means is that the crime scenes, their geographical locations, are never random. They contain information about the criminal. And that's something we can use to catch them. Let me show you how this is done. And I'll do that by taking you all the way back to 19th century London, to the Whitechapel area, the streets that Jack the Ripper haunted. And I hope you can see that here. You have some blue dots there. Those are the crime scenes of the Ripper. So what you do with geographical offender profiling, if you want to catch Jack the Ripper, is that you consider each crime scene a center of gravity, right? And then you weight them all together, but with one important psychological twist. Psychologically, all distances aren't equal, so crime scenes that are closer to each other tend to get assigned more weight. So now, when you weight them all together, you end up with a new center of gravity, and that's the red area there in the middle. That's called a hotspot. And according to the research, there's a 70% chance that our offender will have his home base there. So if you want to catch the Ripper, that's the area to patrol and supervise. And now I guess you're all curious, how is he ever going to tie this back to software? I'm a bit curious myself, so let's have a go at that. But before we do that, perhaps you want to know if this profiling stuff works at all. Because I know Jack the Ripper is a cheap case study to make, right? He was never caught. So who was Jack the Ripper? I really wish I could answer that question. I can't. But what I can do is to look at the main suspects and see how well they fit the profile. So let's start with my #1 personal favorite suspect, Mr. James Maybrick. Mr. James Maybrick was a cotton merchant from Liverpool. And when he went to London to do business, he used to rent a room in Middlesex Street. So let's have a look at Middlesex Street. It's there, right in the middle of our hotspot. So James Maybrick is a pretty good fit for this profile. If you read the news, I guess it was last fall, you probably heard about the supposed DNA evidence against another Ripper suspect, the hairdresser Aaron Kosminski. Now, Kosminski, he probably lived at Sion Square. So let's have a look at Sion Square. As you see, Sion Square is a little bit east of the hotspot. So Kosminski is not as good as a fit as Maybrick. But this just raises an important point about geographical offender profiling. That is important that you keep in the back of your head as we move to the software world. So geographical offender profiling never points to a precise position. What a geographical offender profile does is that it projects a probability surface onto the geography, right? So finally, let's see how this relates to software. And I think that's important because look at it for a moment. Look at the hotspot and consider what we have done. We have taken a potentially vast geographical area and narrow it down to a much smaller area where we can now focus our human expertise. So what if we could do the same for software? What if we could take those hundreds of thousands lines of code and narrow them down to some smaller hotspots where we can now focus our intuition? How can we do that? The first thing that we need is obviously a geography of code. Here's my favorite approach. This is Code City. And in Code City, software systems are visualized as towns. So each package, each namespace becomes a city block. And each module, each class becomes a building. And you probably see that there are some large buildings and some really small ones. And that's because size represents complexity. So the more complicated the code a building represents, the larger the building, right? And what I like about this visualization, it gives us a pretty good idea of where the complex parts are in that code base. But again, that doesn't move us forward. That's just our plain old complexity metrics visualized in a new way. It's useful, but it's not as useful as it could be. So what I suggest is that we add the missing dimension. We need to add the spatial movement. Not of criminals, but of programmers. And that's data that you all already have. We're just not used to think about it that way. I'm talking about our version control systems. Each time we make a change to the software, our version control system records a lot of interesting information. This is a simple example from Git, and you see that each time we make a commit, Git knows who did the change. When was the change done? And most importantly, where in the code did the change took place? Now, this is a single commit for a single programmer. A large system consists of virtually thousands of commits, right? Perhaps hundreds of programmers. So what if we take all that data, aggregate it, and project it onto our geography of code? Here's what it looks like. So you see those red spots glowing up? Those are our hotspots. And a hotspot in this case is defined as complicated code that we have to work with often. So complicated code that we have to work with often. what kind of code is that? What's the consequence of that? To find out, I did a set of case studies, and I would like to present one of them for you. This is a case study done on a fairly large system consisting of 400,000 lines of code. That system was developed by 89 programmers, and I looked at a period of a year and a half. And during that time, those programmers made a lot of changes. So here's what the geographical offender profile looks like. My wife claims it looks like an alien. But it's not. This is 400,000 lines of code. And the first thing that you note, besides the alien, is that I moved back to a two-dimensional representation. And that's because I think it gives us a better overview on large systems. It's also a bit more reminiscent of the real-world offender profiles that we watched earlier. So this is an interactive visualization, which means you can zoom in and out to the level of detail of interest. But even here, on the highest level, we're able to spot a number of hotspots. Now, remember, hotspots were complicated code that you have to work with often. What can we expect to find when we look into a hotspot? To answer that question, I decided to mine a second set of metrics. I decided to look at the bug distribution in that system. And I did that because bugs have this funny property that bugs tend to cluster. Bugs like each other. So in a typical large system, relatively few modules tend to be responsible for the majority of all bugs. And I looked for an overlap with the hotspots. I kind of looked at the predictive value of hotspots. And what I found out was really interesting. I found out that the hotspots identified 7 out of the 8 most defect-dense parts. Even more interesting, the hotspots only made up 4% of the code, yet that code was responsible for 72% of all defects. Or if we turn it around, in this particular system, if you improve just 4% of that code, you get rid of the majority of your defects. And the hotspots show you exactly the parts of your code base that matters the most right now. So, hotspots help us narrow down a large system to the parts that really matter. The parts that we actually work with, where we are likely to get a payoff on our investment that we make in a redesign or improvement. But that's really just a starting point. We can do so much more with this data. And I would like to show that to you by having a look at what happens to our code. What you see here is a picture of a computer program. And I'm well aware that you cannot read the details. That's deliberate. I just want to focus on the overall pattern here. And that's because I'm pretty convinced that we, as an industry, we are actually quite good at writing code. We know what good code looks like. We know about loose coupling, we know about cohesion, we know about the solid principles and all that other stuff that we think is important. So I would claim that our first version of a program typically looks quite good. But then something happens. Let's have a look at that. Whoops. Doesn't look too good. Oh no, oh no, oh no. Oh, gee. What just happened? A program started out so pretty, and then a number of small disasters occurred to it. What are those disasters? What just happened? Well, let me tell you. We started out really well. The second one, that's a new feature. The third one, that's a bug fix. Later on Friday, just before our deadline. And the third one, that has to be when the project lead decided to cut the scope. And then, of course, he changed his mind. So this, my friends, this is time happening to your program. This is maintenance, and that's actually a good sign. It means somebody using your program, and they care enough about it to suggest improvements. Because each one of those disasters represents something that someone thought adds value to your program. So this is a good sign. The problem starts when we continue to build upon that shaky foundation. When we allow our code to decline in quality like that. So what we want to be able to do is to somehow identify those parts of the code base that degrade like that. Here's one way to do it. This is an analysis I call complexity trends. And what I do here is that I pick each hotspot in the codebase, and then I scan through its version control history and measure the complexity of each historic revision of that hotspot. And that allows us to plot a trend in time like that, which in turn allows us to predict the future. And the graph that you see there represents the complexity trend of a single hotspot over 4 years. And you can see that this code had just kept accumulating complexity. Now remember, it's a hotspot, which means we had to work with it often. What do you think happens if we have to work with code often and it becomes more and more complicated over time? I would say it's not a wonder that there's a strong correlation between hotspots and defects. So with a complexity trend, we're actually able to capture that and stop that trend, stop that further decline. All right, so up until this point, I've been pretty much focusing on the technical side, but we have something even more important to talk about today. And that's the other dimension of software development. Software development as a social activity. And I'd like to introduce this part of the presentation by one of the best quotes I know about software development. Code doesn't lie. If we want to know how something really works, we need to look into the code. The truth is there, and it's described in very precise technical detail. So, code doesn't lie, but it doesn't tell the whole truth either. And if we limit ourselves to what's visible in a static structure of the code, we miss a lot of valuable information. And what I'm going to show you now are measures that we just cannot do from the code alone. And the first example is something I call a temporal coupling analysis. So let's see how that works with temporal coupling. So we have a simple system here. It consists of just 3 different modules. And what we're interested in now is the evolution over time. So the first time we make a change to the system, we change the fuel injector and the diagnostics module together. In the second commit, we change something else. In the third commit, we're back to changing the fuel injector and the diagnostics module again. Now, if this is a trend that continues, there has to be some kind of relationship between a fuel injector and the diagnostics module, right? Because they are changing together in time. What kind of relationship could that possibly be? What you will find when you start to investigate those findings is most of the time you will find this. You will find that you have some code over here. You have some other code here. And this one uses that one. So each time you change this API, you have to modify the client as well. This is just plain old physical coupling. And that's indeed something you can see in the code. But remember, temporal coupling isn't measured from code. It's measured from the evolution of the code. And that means you will sometimes find patterns like this, where you have some code over here, you have some other code here, and there's no dependency at all between them, yet they keep changing together over time. How can that possibly happen? Is it some kind of spooky quantum physics thing? Most of the time not. What I usually find when I investigate those cases is a dear old friend. Copy, paste. You have some code over here, copy paste it here, here, and here, and now each time you modify the original, you have to remember to modify the copies as well. So temporal coupling is an excellent way to detect software clones. But there's really so much more we can do with temporal coupling. We can analyze complete software architectures. And I would like to show you one of the examples of that, and then we see the social dimension come into play as well. So this is an example of a pretty simple system. We have 3 different subsystems, and we can measure temporal coupling on a subsystem level as well. If we do that on this system, we actually find out that these 3 systems are coupled in time. Do you think it makes a difference if that system is developed by a single programmer, or if it is developed by multiple programmers organized in multiple teams? Oh yeah, it makes all the difference. And I actually experienced that a few years ago. At that time, I did some work for a fairly large development organization. We were something like 200 programmers. And the first day I got to work, I got assigned a number of tasks. So I picked one of them, sat down and started to work on that one. But I pretty soon noticed, in order to complete this task, I have to make a modification to an API here. It was a really simple change. But that API was owned by a different team. So I walked over to their team lead and asked him if he could do that change. And he went like, yeah, sure, it's a dead simple change. I get started on it right away. Oh, perfect. So I went back to my desk, and then he came back like a week later. Now I'm done. All right, simple change. But I didn't think too much about it at that time. Probably something came up. So thing was, it turned out we had to change that API a lot. And each time we had to do that, the change took at least 1 week to get. At least 1 week. So I figured I really have to find out what's going on here. So I walked up to a team lead once again and I asked him, I mean, sorry, but that change, was it so much harder than you expected? And he looked at me like, no, of course not. I told you it was simple, so why do you ask? Yeah, I mean, it took you a week. And what he told me completely changed how I view software architecture. Because what happened was this. The change was indeed trivial for them to make. But in order to do it, they had to modify yet another API that was owned by a different team. And they in turn had to go to yet another team. And that team had to go to the database administrators. And, yeah, as we all know, that's where change requests go to die. So it turns out, if you have a system where you have a coupling between its different parts, and those are developed by multiple teams, well, you actually have a dependency between people too. And this goes all the way back to one of the famous observations about software development, Conway's Law. I guess all of you are familiar with Conway's. How many are familiar with Conway's Law? Cool, so almost half of you. Great. So I would just cover it really briefly because Conway's Law has received a lot of attention over the past years. So Conway's Law is basically the observation that the way we are organized tends to be reflected in the kind of software we design. So the popular saying, if you look it up in like the Hacker's Dictionary, is that if you have 4 teams designing a compiler, you will get a 4-pass compiler. And that's kind of the fun, cynical way to look at it. But the cool thing with Conway's Law is that Conway's Law has just as many interpretations as there are research papers about it. So we can actually pick our favorite here. And I always use Conway's Law in reverse. And there you start with the kind of system you're trying to build. And then you look at it, and then you design your organization based on that system. How should we be organized to make this happen as efficiently as possible? And I do that because when Conway's Law is used in reverse, it becomes a useful organizational tool. But, I mean, most of the time, we aren't doing new software architectures. We have existing systems that we need to modify, that we need to improve, that we need to correct bugs in. So how can we use Conway's Law on legacy code? The first thing I always suggest is that you start by trying to understand what you have today. How well does your current architecture support your way of working? And one way to do that is by using something I call communication diagrams. So communication diagrams are created out of the evolution of your code base. So what I do is I scan the complete source code repository, and each time I find a module where 2 different programmers have contributed, those 2 programmers get a communication link between them. And then I continue to scan, and a 3rd programmer comes along, and if she has worked in the same part, then she gets a communication link as well. So over time, this allows us to build up a complete graph over the ideal communication paths of our organization. And I say ideal because remember, this is mined from how the code was actually created. There's nothing here to suggest that that represents communication that actually took place. So what you want to do is to take your communication diagram and compare it against your formal organizational chart. And any discrepancies really have to be understood. So let's have a look at some typical findings, what you can expect to find when you do that. According to Conway, this is what you would expect to find. And what you see there, this simple example, you have 3 different teams. And you see that most lines are between members of the same team. And that means they work in the same parts of the code. They share the same context. And that's something that actually makes communication so much simpler and cheaper. So that's what you want to see. And you also see that you have the occasional programmer that works in a different part of the code base. And that's just a sign that a certain degree of cross-pollination is a good thing in software development too. This is knowledge sharing probably. People that are rotating teams. So this is where you want to be. Let's look at the opposite side of the spectrum. Do you want to see a complete disaster? Here we go. So this is a story about a company. And this is a company, they were in a very good position. They were going to do a new product. And they were in a good position because they had done something very similar in the past. So they knew this will take us 1 year. Of course, someone came up with the idea that, yeah, 1 year, but you know, we have this really cool trade show in just 3 months. Can't we do it in 3 months? All right, so how do you take something that's expected to take 1 year, compress it down to just 3 months? It's so easy. Just throw 4 times as many developers on it. And I promise you, this was a really fast-paced project, right? So the initial architecture was set, and 25 consultants were recruited in shorter time than it would take you to read the Mythical Man Month. And they chose to organize them in 4 different teams. How do you think their communication structure looked like? And this is the actual data I was allowed to use. This is the real data from the real project. Here it is. That figure looks kind of cool, doesn't it? But let me assure you, there's nothing cool about it. This represents chaos. This is complete communication anarchy. Because if you have a look at it, you will see that, yeah, sure, within each team, the people do work in the same parts of the code base. The problem is everyone else does that as well. So this is not 4 different teams. This is virtually one giant team of 29 people with artificial organizational boundaries between them. And I didn't work on the real project, but I came in afterwards and did a post-mortem analysis. And I get to talk a lot to the developers, and they told me a lot of interesting stuff. Virtually all of them complained about quality. They had a lot of defects. The second thing that everyone told me was that the code was hard to understand. Because even if you wrote a piece of code yourself today, 3 days later it looked completely different because 5 other developers had been working on it in the meantime. And another thing that turned up was that they spent a lot of time merging different feature branches. They could spend literally days, sometimes even a week, merging different branches. If you look at that communication diagram, you see that no, they didn't have a merge problem. Their problem was that their architecture just couldn't support their way of working with it. So if you find yourself in that situation, there's unfortunately just 2 things you can do. Either you need to change your architecture to support the way you want to work with it, or you need to change your organization. So people, please align your architecture and your organization. Your code is going to thank you for it. All right. So the project I just told you about, remember that the programmers complained a lot about bugs. And that shouldn't be surprising given what we actually know about software bugs. It turns out that the number of programmers behind a piece of code is one of the best predictors of the number of defects you will find there. So in general, the more programmers that have contributed to one module, the more quality issues in that module. So I started to think, yeah, well, again, this is data that we actually could mine from a version control system and identify those components at risk for defects. Here's one way to do it. This is a visualization called fractal figures. And fractal figures works like this, that you consider each module a box. And each programmer gets assigned a color. And the more they have contributed to the code, the larger their area of the box. So you see an example here of 4 different modules. And you see that the red-orange developer and that one is actually green on one. The green, grayish a programmer, they have written most of the code. But if I'm after excess parallel development, I would go for the second module there, because you see it has contributions from a lot of different developers, many small contributions. And when you see a pattern like that, you need to understand why. And I promise you, if you look into that code, you will find that code changes for a reason. The reason that module attracts many programmers is probably because it has many reasons to do so. It has too many responsibilities. So this is a good starting point, but we can do so much more with fractal figures. As you see, fractal figures makes it pretty easy to identify the knowledge owner, the main developer behind each module. And if we have that information for each module, why don't we project it onto our static geography of code? That would allow us to build up a complete knowledge map of our code base. Here's how it looks. And again, this is real data from a real project. This is the Scala project, and you see a part of the compiler there. And this is something you use to simplify your communication. So let's say that it works exactly the same. Each programmer is assigned a color, and what you see is the main developer. So say that you join the Scala project and you want to know something about the backend in your upper right corner. Well, I would say that it's a fairly good chance that the light blue developer may know something about it. And if she doesn't know, perhaps the green developer knows. So this is something you can use not only to simplify communication, but also to ensure that you invite the right people to code review or discuss a proposed design change with the right people. But we can do even more. Instead of focusing on individual developers, why don't we aggregate them into teams? That would give us a way to evaluate Conway's law. Here's how it looks. So now the colors represent teams. And you see, according to Conway, this actually looks pretty good. You see the red team, they have their own subsystem where they pretty much can work in isolation. And the pink system also have their own system, so that also looks fairly good. But down below, you have a fairly large subsystem with contributions from all three teams. And again, when you find something like that, you need to understand why. And it could be as simple as this organization maybe just lacks another team to take on a shared responsibility. But I guess that most of the time what you will find is again that code changes for a reason. The reason that subsystem attracts three different teams is probably because it has three reasons to do that. It would perhaps be better off split into three different parts. And when we have a knowledge map of teams, why don't we overlay the result of a temporal coupling analysis? And that allows us to spot those expensive modification patterns that ripple through the organization. You know, like the story I told you about a while ago, where a simple change took 1 week because it rippled through the organization. Here's how you identify those. And we already touched upon the communication diagrams, but those communication diagrams, those are virtually your social network of code. And when we talk about social networks, you will find that the 80-20 principle holds in code bases as well. You know, it's true on Twitter, it's true on Facebook, and it's true in code, that 80% of the content is generated by 20% of the members. And I see that all the time. I have analyzed literally hundreds of different source code repositories. And you see the developer on the right, he has a lot of communication going out. So these people, they're probably core developers. They're key players. They know the code base inside out. And you have that in all organizations. Perhaps they are you. So what would happen if you suddenly left? If you just walked out the door on a day job, decided to quit, or you get pulled from a current project, what would the consequence be? Well, we would obviously get a knowledge gap. How big? Most of the time we have no idea. But using this data, we can actually find out. Here's what it looks like. So you see those orange dots there? In this case, they don't represent hotspots. No, they represent abandoned code. That is, code that's written by a developer who's no longer in the organization. And this is something you can use as a technical leader or a technical manager to reason about the knowledge distribution in your code base. And when you do that, you will sometimes find things like this, where you have an entire abandoned subsystem. And again, that's something you can use as part of a risk assessment, because it is an increased risk to modify code that we no longer understand. All right, I'm almost done now. I just want to summarize it for you before we go to the questions. So I think that the ideas from forensic has a lot to offer in software development too. We have seen how hotspots help us identify code that's hard to maintain and code at risk for defects. And we have also seen that these analyses, they go way beyond code. And they let us reason about things that we haven't really measured before. Things like knowledge distribution, and we can even evaluate the organization with respect to our communication paths contra our way of working. So this is something you can use in a tech lead position to improve and simplify. And this is a large area, and this presentation has really just scratched the surface. So if you want to dig deeper, feel free to send me an email or have a look at my blog, where I regularly write about this stuff. And of course also get the complete book that goes into all this stuff in much more detail. So now, before we go to the questions, I just want to take this opportunity and say thanks a lot for listening to me, and may the code be with you. Thanks. Thanks.
There are some questions, Adam.
Oh, great.
So, which tools support extracting all those data from our code base?
So, which tools? I'm actually using my own tools. And the reason for that is, when I started out with this kind of stuff like 5 years ago, there was virtually no tooling support beyond Academica. So I had to write my own tools for that. And I'm still using them. And if you go to my homepage, you will actually find a link to my GitHub page, because I do open source a lot of these tools that I use. So they are available there to help you get started. And I think we will see a lot more happening in the tooling area, because I actually just launched my startup, where I will be focusing on delivering professional tools around this area. So I hope I have some really exciting stuff coming up soon.
Right, so that also answered the next question about open source tools. You do have that.
I do have them, yes, and I will continue to maintain them.
Great. So here's another one, that's a tricky question and long. Would you agree that your tools will work only for mature projects with stable crew developing them? You cannot predict the future or compensate for people joining and leaving the team.
It's partly true. I mean, there are basically two different sets of analyses. You have the technical analyses like hotspots and temporal coupling, and those are useful on all kinds of projects. Even those one with quickly changing stuff, it doesn't really matter. They are even more important there, I would argue. But things like a communication diagram kind of loses its meaning if people rotate teams a lot and new people come out and leave. But I still think it's useful to have a knowledge map, at least for the abandoned code.
Right, so do you have any tips on how we can utilize that in an agile environment, where in at least my team, we do not encourage code ownership? Thanks.
All right. So how can you use this in an agile way? Well, what I've been doing is that at the end of each, if you're doing something like iterations or sprints, at the end of each iteration, I used to print out a hotspot map and give it to the test leader. And the test leader used that to focus their exploratory testing efforts to the areas that were most likely to contain the defects. And we actually got a huge return on that simple investment. I also think that it makes sense to measure temporal coupling at the end of each iteration and do something. Use a real low-tech, dead simple technique. Just print out a map of your temporal couplings, nail it to the wall, and in the next iteration you do the same thing. And that simple technique allows you to spot architectural decay. And that is when you suddenly get dependencies in time between different parts of the code base located in different subsystems. So that's something I really recommend.
What about projects with no source control? They do exist, unfortunately.
They do? Wow. Wow. Yeah.
In Denmark, they do.
My tools won't be able to solve that, unfortunately.
Right. So, which tools did you use for the visualization?
Oh, again, that's my own tools. And I do the visualizations. I use mostly D3, the JavaScript framework, but I also do a lot of them in Clojure, using a framework or a library called Quill, which is a layer on top of processing, which in turn is a creative coding environment. And it's really fun. So please pick up processing. It's just so fun to code in.
Right, I think the last question now. How do you convince management to reshape the organization to fit the architecture once you've identified the need for it?
Wow. If I would know the answer to that question, I wouldn't be here. I would be out there on my yacht or something. So I'm sorry, I really don't know that. But what I do know from experience, I do this kind of analysis in different organizations, and management do tend to react to what they see, because you get hard figures that shows you that this is something that actually costs you money. So management tend to be quite receptive to this kind of analysis. That's my experience, at least.
Right, so remember to vote, and you can still add comments, and I'll send them to Adam in an hour or so. Thank you very much for listening, and thank you to Adam.
Thanks.